Okay, so two parts. So the first part is you have the pyridine, which is the weak base. We know the pKb of the pyridine is about 8.75. So what is the pH when the concentration of the pyridine is actually 0.280 moles? So first, what we can calculate is the Kb. That's equal to 10 to minus pKb. So that's 10 to minus 8.75. So in this case, that's equal to 1.778 times 10 to minus 9. And then we can write down the general expression for the pyridine to dissociate. So we don't have to write down the structure of the pyridine. We can simply use B to indicate BOH to indicate a base, right? So for the pyridine, let's say it's BOH, it dissociates into the cation and the OH minus. So we can start making ice table here. So initially it says you have about 0.28 moles of the pyridine, and there's no cation and no OH minus. That will be changed. Let's say X moles of the pyridine dissociates. That will generate X moles of cation and X moles of OH minus. So in the end, you have 0.28 minus X and X here. So now what we can write down is the expression of the Kb here, which is concentration of the cation times the concentration of the hydroxide, the OH minus group, over the concentration of the pyridine at the equilibrium state. So that's actually equals to X squared over point, in this case, 28 oh my god, 0.28 minus X. So in this case, that's equals to the Kb value, which is 1.778 times 10 to minus 9. So in this case, we can make some assumptions, right? The X should be very tiny because you can see the Kb is very small. So that becomes X squared over 0.28 equals to 1.778 times 10 to minus 9. So the X squared, X actually equals to square root 0.28 times 1.778 times 10 to minus 9. So let's do the calculations. So we'll find X here equals to about 2.23 times 10 to minus 5. So this X is actually the concentration of the OH minus. So in this case, we can calculate the POH. That's equals to minus log the X. So that's actually equals to 4.65. So the pH will be 14 minus POH. That's equal to 14 minus 4.65. That's about 9.35. So this is the first one. So the second one, it says you know a pKa of the reaction is 4.2. For the benzoic acid, right? Now you have the benzoic acid. So the benzoic acid, you know the pKa here is about 4.2. And you also know that in a 0.53 moles of the solution, so what is the percentage of the molecules that is ionized? So same here. First, we can calculate the Ka for the acid is 10 to minus pKa, 10 to minus 4.2. That's equal to 6.3 times 10 to minus 5. So for the benzoic acid, we use Ha to indicate. It dissociates into the proton and the A minus. So in this case, what we calculate here is draw the ice table here first. It says you have initial 0.53 of the acid. You don't have any proton and A minus, the anions here. And X will be generated, right? Will be consumed, so will produce X more proton and X more the A minus. In this case, the HA will be 0.53 minus X, and proton is X, and A minus is X. So in this case, you'll find the X squared over 0.53 minus X equals to 6.3 times 10 to minus 5. So the X squared actually equals to 0.53 times 6.3 times 10 to minus 5. So that's about the X here, actually about 5.7784 times 10 to minus 3. So we want to know the percentage for the ionization. So that's X over 0.53. So that's 5.7784 times 10 to minus 3 over 0.53. So that's actually about 1.09%. And this is the answer.